Mechanics is the study of motion and the forces that cause motion or changes in motion. Um, and in 1687, Isaac Newton laid out the foundation for what we call classical mechanics or Newtonian mechanics in his book, Mathematical Principles of Natural Philosophy. In it, he laid out three laws, which create the foundation for classical mechanics. So in this video, we'll discuss his first two laws. So Newton's first law is very similar to Galileo Galilei's law of inertia, and what it says is that an object at rest remains at rest, and an object moving continues moving in a straight line with a constant speed unless the object experiences some net external force. So that's one way of saying it. So these are not two different definitions. There's just two ways of saying the same thing. So another way of saying this is that the natural motion of any object is constant velocity, and in order to change this motion or this velocity, you need a net external force to do that. So we have here this box. This box is just sitting here, and if there are no forces which act on it, then it would stay stationary. However, if we apply a force to it, then it would. Let's put another box here. If we apply a force to it, then it moves off, and it moves off at a constant velocity. Remember, the velocity is a vector, and so there are three ways in which it can change. It can speed up, it can slow down, or it can change directions. So when this object speeds up, obviously it's at rest, and then it speeds up in this direction, then it experiences an acceleration or a net force. Also, if it changes direction, it experiences a force as well. So if an object speeds up, slows down, or changes direction, then it experiences some net external force. If we have no force acting on it, let's see. Let's say that we have this box here, and so actually, let's say there are two forces acting on it. There's a weight which acts downwards, and there is a normal force which acts upwards. And it's sitting on a surface here like this. So if the magnitude of the normal force is equal to the magnitude of the weight, then this net force would balance out to be zero. And so this figure would be the same as a box sitting on a surface with no forces acting on it whatsoever. These would be equivalent. So no net force causes no motion, and same as just having zero forces whatsoever. So if there is no net force, then there will be no change in velocity. Right? So we have, if the net force, or the sum of the forces, are equal to zero, then this means that the change in velocity is equal to zero, which means that the acceleration is equal to zero. And so anytime that we have a net force equal to zero, this is a state we call equilibrium, because the object will continue moving at a constant velocity. So equilibrium means that the acceleration, equilibrium means that there is no change in velocity, which therefore means there is no acceleration, which means there is no net force acting on it. That isn't to say there are no forces whatsoever acting on it. In this case here, we had a weight acting downwards and a normal force acting upwards. There were two forces acting on it, but the net force is equal to zero. So this is an equilibrium. And the object doesn't have to be stationary either. We can have an object moving along at a constant velocity, and as long as that velocity is constant, then the object is in equilibrium. So if this moves on at a constant velocity, then it's in equilibrium. So if there is no net force, then there is no change in velocity, and we call this no net force and no change in velocity equilibrium. Before we get into Newton's second law, we need to talk about what inertia is, which came up in Galileo's law of inertia there. So we know just from everyday life that if we have a small box maybe made of styrofoam or something, and we have a large box maybe made of steel or something, and we apply a force to the styrofoam box and we apply a force to the steel box, then the styrofoam box is going to move much more easily. Its velocity is going to change much more easily than the steel box. So this resistance to a change in velocity is what we call inertia. The greater the resistance to a change in velocity, the greater the inertia. So we would say that the steel box has more inertia than this styrofoam cube. Okay, but this is a qualitative description of an object's willingness to change velocity. If we talk about linear inertia, so if I refer to inertia, I'm actually just referring to linear inertia. We will discuss rotational inertia later on. So if I just say inertia, it means linear inertia. I'll specify rotational inertia when we get there. But linear inertia is a quality of something. But we can quantify this by how much material makes up the object. So this is quantified by the mass of something. Quantified by the object's mass. So if we talk about the linear inertia of an object, that is the same as its mass for all intents and purposes. And what Newton's second law says is that the acceleration of an object is directly proportional to the net force applied to it. So we have here the acceleration is directly proportional to the net force applied to it and inversely proportional to the object's inertia. Object's linear inertia. And we said in the previous video that the net force is the same as the sum of all the forces acting on it, and the inertia is the same as the mass. The linear inertia is the same as the mass, and so we have the acceleration is directly proportional to the sum of forces and inversely proportional to the mass. Typically, we write this as the sum of the forces are equal to the mass times the acceleration. And this is Newton's second law. Force equals mass times acceleration. And Newton defined 1 Newton to be 1 Newton is equal to the amount of force required to accelerate 1 kilogram of mass at a rate of 1 meter per second squared. And so the units of a Newton are a kilogram meter per second squared. If we had here 5 kilograms instead, 5 kilograms accelerated 1 meter per second squared, we'd have 5 newtons of force. If we had 1 kilogram accelerated 5 meters per second squared, it would still be 5 newtons of force. If we had 5 kilograms accelerated at 5 meters per second squared, we'd have 25 newtons of force. So that's the definition of 1 Newton there. Now we know that we have, well actually, if you think about the acceleration here for a minute, we know that if we have a constant acceleration, then we can use the kinematic equations. And so then, since it's a force that causes acceleration, we can say that if we have a constant force, we have a constant acceleration, and so then therefore we can use our kinematic equations as well. So we can use the kinematic equations anytime we have a constant force. And when we use the kinematic equations, we broke our acceleration into x and y components, acceleration in x and acceleration in y. And we know that we can break any vector, any net force into a couple of different forces, and so we can break this into components as well: the force in the x direction and the force in the y direction. So typically, the way we'll write Newton's second law is that the sum of the forces in the x direction is the mass times acceleration in the x direction, and the sum of the forces in the y direction is the mass times acceleration in the y direction. And so this is Newton's second law in component form. So the way that we'll apply this to problems involving Newton's second law, let's say we have a box on a table and we have a weight which acts downwards, and we have a normal force which acts upwards, and then we have some other force down like this. I'll call this force 1, and another force up like this, force 2. Then, in order to find out, and this box has some mass m, in order to find out what the acceleration of this box is and describe its motion, we would first break this up into components. So I'd have here f2x, I would have f2y. I'd also have f1x, and I'd have f1y. And so then we can sum the forces in each direction respectively. I would have a sum of forces in the x direction would be equal to f2x plus f1x, and these are my only forces in the x direction. So this must be equal to the mass times my acceleration in the x direction. Similarly, we would do this in the y direction as well. Sum of forces in the y direction, we would have here the weight plus the normal force plus f1y plus f2y must be equal to the mass times acceleration in the y direction. When we actually plug these in, we'll be careful with our sign conventions for all of these, positive or negative, but in general, this is the way that we will approach Newton's laws problems. So Newton's first law says that equilibrium is an object's natural state, and equilibrium means there is no acceleration, so the velocity remains constant. And Newton's second law is really just this equation, or these equations: the force is equal to the mass, the net force equals the mass times the acceleration.